will form the fulcrum for the entire workshop. So is what we are all interested about. So I welcome Mr. Harvind Singh Chadda. So he has been working as a data scientist in ThoughtWorks. He has around 7 years of industrial experience. Mostly his focus has been on deep learning related domain and technologies. So off late, like he's involved in Vakyansh. So he's been developing speech recognition systems for systems in 23 Indic languages. And of course, in one of the competitions they participated last time at IIT Madras, they came uh, uh, top one in English ASR challenge. Even this time they've participated. I saw them in the leaderboard. They've come top in many of those competitions, thanks to the kind of system that they've developed. So the very reason we have gathered here is to get the knowledge from them. How do we build such robust ASRs in Indian languages? So then prior to that, like Harvin has worked as a technologist in Wipro CTO team, where again he has built a computer vision based system, especially with reference to the laptop repair. So he has also worked as a specialist programmer at Infosys Advanced Technology Group, where mainly his focus was on developing object detection systems for self-driving cars. So imagine it was developing in the year 2014 to 2019. So he has experience working in deep learning in all vehicle vision, natural language processing, and speech. Basically, his interests are to leverage power of AI in healthcare and finance domain. He has also authored a book called the Applied TensorFlow and Keras Workshop, Build a Bitcoin Price Predictor. So, I mean, what more we can ask regarding his profile? So he's an excellent person for us to delve deep into this wave to wake, and let's learn more things from him. Thank you, Mr. Harvin, for accepting our invitation. Over to you.
Hi everyone. Thank you, Deepak sir, for that introduction. So, in the first half of the session, we'll cover like why there is a need for us to actually learn Wave 2 and then in the second half of the session, we'll learn a high-level introduction and a little bit of more detailed introduction of how Wave 2 works. And in the later part of the day today, we will actually understand how to train your own models using Wave 2 on the experimentation platform that we have built. Okay, so I'll start sharing. So are you able to see my screen?
Yes, sir.
Okay. So I'll quickly go through why there is a need for Wave 2 So first of all, I mean, let's start from the basic beginning. I mean, what is speech recognition? I mean, we have gathered around in this summer school to understand speech recognition. So what does, I mean, in layman terms, how does it actually works out? What is speech recognition? So speech recognition is getting a computer to understand spoken language. So it means like we want to convert our input speech to text. So speech recognition is also known as automatic speech recognition, ASR, or speech to text, STT. So I mean one thing but has multiple names. So there is a lot of polymorphism going around and people often get confused like what is ASR, what is STT. It all essentially means the same. Okay, so that is a bit about speech recognition. So what is the objective of this 8-step project? So the 8-step project that we are doing at ThoughtWorks, it means that we want to focus on 23 Indic languages. We are saying that we want to create automatic speech recognition models for all the 23 Indic languages present. And we want to open source as well. And we just don't want to create models. We want to create the best models in the industry. We want to create the state-of-the-art models for all the Indic languages, right? And then the next question that is quite often asked to us is, why are you open sourcing a lot of stuff? And then the answer to that is because we want to enable the researchers and the new startups to go local. I mean, to focus on local thing, because there is a huge untapped potential in the local market, in the local languages that can be further used. And cloud services like Google and Azure also have these speech to text services, but in order to use them, you need to pay them, and there is no open source state of the art things that are available at the moment with us for our languages. So that is why we took up this mission to actually create models for our languages that anybody can use ground up without even paying anything, without just trying. And so we wanted to quicken this research and development of products in local languages. Okay, so then it comes like, what are the problems with speech recognition? Because see, there is a lot of advancement recently happening in AI in the field of vision and NLP, but speech started picking up recently from 2020 onwards, or maybe just 6 months or 8 months before. So what are actually the problems? So the problems are huge with speech, actually, if you ask me. So it's very speaker agnostic. I mean, see, suppose let's take an example of a language like Tamil. So it is being spoken by 70 million people. So if you have to create a system that can actually recognize the voices and understand what they want to say for 70 million people, you need to have a very robust training data. Okay, and different speakers have different dialects, different speakers have different pitch, different speakers have different volume, the way of speaking is also different, and the environment is also different. I mean, my laptop mic is different than your laptop mic, my background noise is different than your background noise, right? So it is kind of very difficult to actually solve this problem. In if suppose if any you're solving any vision problem, let's say you want to detect the COVID-19 cells from a lung X-ray. It's still, I mean, you have to detect something within an X-ray, like what is the outlier and how this is COVID or not. But in speech, I mean, the possibilities can be endless. I mean, if you just map all these parameters together, you will never be able to create a very robust data set that will have each and everything about different speakers, different dialects, different pitch, and different volume. Okay, so it's very difficult to constrain this problem. Okay, and then, I mean, how do we frame this as a data science problem? I mean, because different problems have different aspects, right? What is the data? So every data science problem has three things. So one is like input data, then the algorithm that is black box to most of the people who actually use that algorithm, and then the output. What is the output expected? So in speech recognition problem, the input is speech plus text. I mean, a lot of people would already know this. I'm repeating this, but it is required for the later understanding of this module. Okay, so the input is speech plus text. And this is only when we treat this problem as a supervised learning problem. So in supervised learning problem, what we have is we already have the labels for the text that we are going to predict, for the audio that we are going to predict. Okay, so you have some audio, you have the corresponding labels that are present in the audio, I mean the text, and then there is a deep learning algorithm, and the output is only text. Okay, so I'll go through two approaches that we went in this project when we started and how it is going. Okay, so the approach one was like to treat this as a supervised learning problem. Okay, so we wanted something based on deep learning, because Kaldi based approaches do not scale very well, because as I talked, like there are different things like different dialects and all. So as as we go into, I mean, from 2014 onwards, we are generating a lot of data, a lot of speech data, or audio data, video data. So the data is present in numerous amounts, and deep learning has a property that if you have a huge amount of data, then it is bound to perform much better than the traditional algorithms. Okay, so we wanted to have a deep DL based approach. So the first POC, we decided to create ASR model for the most spoken language, that is Hindi in India, because close to 57% of the population speaks Hindi. So we tried a deep learning algorithm called DSpeech 2, which was released by open source by Baidu Research, and they created an end-to-end speech recognition model in English and Mandarin. So I think yesterday Anirudh also covered a bit about this. So we took this algorithm and we tried to train a model. So since this was a supervised learning problem, we needed to have a label data. For example, an audio clip and a corresponding transcript, as we have already discussed. And the next question was, how much data? How much data do you need to create a system, I mean a production ready system? So one thing is research, one thing is production. Okay, so our focus was production. So how much data do you need to create a production ready system? So according to our research, we found out that you need at least 10,000 hours of label data to have a good system. And this 10,000 hours is not just 10,000 hours. There are a lot of other properties as well. Like one speaker cannot have more than 30 minutes of data in the training set. So if you go by this logic, to get 10,000 hours, we needed 20,000 speakers. Okay, and we also needed the gender diversity. You cannot have 10,000 hours only in the male voice. You need to have a female voice, and you need to have different dialects also. You need to have different people, like how they speak. You need to have different people, like how they I mean with different pitches, right, and different environments. So all these things were variable. So we needed 10,000 hours, and we needed about 20,000 speakers. So this was where we hit our first roadblock in the project. Okay, because we were not able to get, even for a language like Hindi, we were not able to get 10,000 hours of label data, because the recent advancements in the speech, there is I mean very less advancement in terms of data sets for speech. Okay, so as I said, Hindi is the most spoken language in India, but still we do not have enough label data for Hindi. So what was the solution? So we said, let's create our own data. Okay, so the objective while creating the data, as I have already discussed, we wanted to have sufficient speaker diversity. We said like a maximum of 30 minutes from one speaker, and we'll target 20,000 speakers in those 10,000 hours of data. And we will have utterances with maximum duration of 15 seconds. So this was again one requirement, which was basically based on the due to the hardware limitations of model training. You cannot have an utterance that is greater than 15 seconds during the model training step. So this came as a constraint from the model training phase. Okay, and then we have the utterances with we said like, okay, we'll have utterances with very little background music and noise, and we will induce our own lab generated music or noise. And then the final step was we wanted to create a near perfect transcript from the utterance. Okay, so the first thing is identify the audio source, and the second thing is have a balanced, I mean the gender ratio is balanced, and the third thing is that we don't want maybe more than 30 minutes from a particular speaker. Then the fourth thing is that we want to have a maximum utterance of 15 seconds and with no or very less background noise. So the next thing was how to create the data. Then we started creating our own data pipelines, which I'm really sure that Rajat would have covered in the previous week's session as well. Okay, so I'll touch base just a little bit just to revise the concept, because these are very important to understand the functionality of Web2Vec that is coming just now. Okay, so the data pipelines were covered in 3 steps. So the first step was finding open source data, and the second step was generating the label metadata, like what is the number of speakers, gender, and the third pipeline was the third part was to create transcripts for the data. Okay, so suppose if you get a 30 minutes long audio from a YouTube or something, we had a first step called VAD, which was voice activity detection, which used to break down a video on the detection of a silence. Okay, so this 30-minute long audio would be broken down into utterances, maybe n utterances, and these utterances can have variable length. So utterance 1 can have a length of maybe 2 seconds, utterance 2 can have a length of maybe 4 seconds, and utterance 3 can be 6 seconds, and so on. But we made sure that these utterances are less than 15 seconds, because that was our limitation from the training side when we started. Okay, so then we had something called as signal to noise ratio. So we said that we'll pass each utterance to an SNR, which is an algorithm which detects whether the signal is noise or not noise. So we do a little bit of classification here by using the SNR utility to classify every utterance as noise and not noise. And then whatever is not noise, we used to pass that through Google STT or Azure STT to get the final transcripts. Okay, so if you have 30 minutes long audio, it will be broken down into n utterances. The n utterances will be passed through SNR to get the utterances that are not noise, and those not noise utterances are passed through Google STT to get transcripts. So here we have a pair of
Arvind, sorry. Will we do some exercise wherein we'll pass 1 or 2 files
Mhm.
to the Google STT or Azure STT and
So
get the transcription just for the practice sake? So participants can go back home and generate the transcripts for their respective languages. Is that fine?
I think it was. It might have been covered by Rajat in the previous week. I'm not sure because I was not there in that session. But the pipelining part was present in the previous session, because this API also request. I mean, the API. You need to get some special request to run the API from Google
Okay.
Answer, right?
Okay.
Yes. So
And
I'm
it
not
is a
sure if
paid service, right? Is it?
yes, it's a paid service. Yes.
And we are running like we are getting this transcript using API, so it is dependent on some API, so it may not be 100% is correct, right?
Yes, yes. It cannot be 100% correct. So that is why we need to diversify our APIs as well. So we are not 100% dependent on Google. Okay. So what we are saying is, let's pass 25% of the data through Google, 25% of the data through Azure, then 25% of the data through AWS. Because I'll come to a point why we did so. Because the reason here was we wanted. If you create your 100% data just from Google, then your algorithm will also do the same mistakes that Google does. Okay. So, but if you are able to diversify your sources of getting labeled data, then the deep learning is so powerful that it understands that this is a mistake that is there in the transcript. So this is what we need to avoid.
And how
Okay.
we are managing all this, like how we are diversifying this data?
See, in deep learning, if you have a large pool of data, okay, so if you have like 6,000 to 7,000 hours of data, and 2,000 hours is passed through Google and 2,000 hours of passed through AWS, then you just give the algorithm time to figure it out. Okay, so that is the beauty of deep learning, because it is very much. It can understand noise very well. Okay, so even there can be mistakes with hand labeling. So suppose I am a Hindi transcript, I do Hindi transcripts, and you also do Hindi transcripts. I know something about Hindi that you might not be knowing. Okay, so I may transcript in a particular way, and you may transcript in a particular way. Okay, so I'm talking about the spellings. Okay, so in that case also the deep learning algorithm has to figure out, okay, what is the correct way. And if one person does the 100% of the thing, then there is a problem. Okay, so diversification here happens just on the basis of volume on the pipeline, that if we are running 100 hours to Google, then we'll run the 100 hours on Azure.
Hello, sir.
Yeah.
Sir, you are making transcript from those occurrences. So if I take a new language that is not present in Google STT, then will it be able to transcript in such a efficient manner?
Yes, so that's a very good question, because if the Google STT is not present, then we do not have data, right? So what then we do then? We created a portal for crowdsourcing data. So we are saying that please come and donate your voice. So we have created a portal called Vakyansh, in which people can come and donate their voice. So what we are showing them is, we are showing them sentences, and we are giving them a utility to record what is there on the screen. Okay, so once we have that, maybe tomorrow in the second half, I'll show you a small demo on how we actually do that, how the crowdsourcing portal works. Okay, but for languages for which we do not have a Google STT or Azure STT, there is a problem. Okay, and there is a problem, and I'll talk about that problem, like why we did what we did about that problem. But the temporary solution that we had was to crowdsource data, to ask people to come forward and donate their voice.
So then we have to wait for it now after
Yes.
a certain time, when some large amount of donation will be done, then we can go for a model design.
Yes. So that is why, that was one of the reasons why we switched our algorithm. So right now we are still in approach 1, where we are treating this problem as a supervised learning problem. Okay, so right now I'm not talked anything about wake to wake. Okay, so right now you just have to understand, for every language we need 10,000 hours of labeled data, which might not be possible for low resource languages like Odia or maybe Santali, Bodo. For them, we do not have enough native speakers, right?
While donating, people can speak multiple languages. So how you are managing that thing also?
So we have a portal where people can come and donate their voice, and then we have a validator portal where you can come and validate whether whatever is spoken in the sentence is right or wrong. Okay, so if we get 3 votes, so one sentence is shown to 3 validators. If we get 3 votes from the validator that this is the correct mapping of audio to text, then we take that sentence, or we do not take it.
That is also manual, like crowdsourcing only.
Yes, crowdsourcing only.
And Harvind, this is post the transcription that we get from Google STT and all the STT, is it?
Yes.
Okay.
Okay. So right now we are still in approach 1, where the problem is we need 10,000 hours of labeled data. Okay, I have not gone to wake yet, and I'll things will magically change when we'll move to wave to wake. Okay, so the next step was modeling data. So we were able to create 4,500 hours of Hindi labeled data in 4 months using the data pipeline that we created. The data pipeline that we just talked about, we were able to create 4,500 hours of Hindi labeled data. I mean, in 4 months, we were only able to create 4,500 hours. Okay, so that is the key point here. And then we trained a model using the open source PyTorch implementation of this speech. And we were able to get a WER of 35 on test set, while the WER of Google ASR was around 30 on the same set. Now you will ask me, what is WER? Okay, so WER is a metric. Is a metric to understand how good your speech recognition model is. Okay, so WER stands for word error rate. Okay, so it means that how many insertions, deletions, and substitutions are required to make the 2 strings equal. Okay, so if you have a model that predicts text, and if you have a ground truth, then you have 2 texts. Now you want a metric to compare 2 texts. Okay, So to compare two texts, there is a metric called WR which tells you if you need to make these two texts equal. So these are the number of insertions, deletions, and substitutions that you need to do. Okay. So a lower WR means the speech recognition model is better. Okay. And it is based on a DP algorithm called edit distance. Okay. Which is, I'll pass on some resource to understand that algorithm in detail if you want, but if even we won't dive in that detail, but it's based on edit distance algorithm. So for example, if the original sentence is that this deck is for the global community call, and the predicted sentence is this deck is for global community call, then you'll find out that in the predicted, the is missing before global, the spelling of community is wrong, and there is an insertion with a. So the WR here is 3, basically on just based on the fact that the algorithm did 3 mistakes in the predicted one. Okay. So this was our approach 1. So we created for 4,000 to 4,500 hours of data, and we created a deep speech model, which was good enough to compare with Google. And we deployed the model as well, and we tested out, and the model was working good. But what we realized from approach 1, which we all were discussing a few minutes back, scale. We took 4 months to create 4,500 hours of data. We don't have so much time in today's world to create so much data, okay? And we do not have so much native speakers. As I said, I mean, Bodo, Santali, these are very low resource language. You cannot have 10,000 hours of data in Bodo or Santali with 30 minutes max a speaker. It is not possible. Even with a crowdsourcing portal or something, it is not possible to create huge amounts of data. Okay, as I said, I mean, and not all languages have Google STT or Azure STT or AWS STT available. So we cannot create transcripts for every language present, and we cannot create data for every language, every Indic language. Okay, so there were 2 steps that we needed to improve upon. The first step was to make the data pipeline as much automated as possible, like data discovery, the identification of gender, the identification of language. So I hope that in the previous week, Rajat has covered about how we are identifying gender, how we are identifying speaker, and yesterday Anirudh covered about how we are identifying the language using a deep learning model, right? And the second learning, which was very important in the context of today, which was like change our deep learning algorithm so that the learnings from one language can be transferred to other language. So like transfer learning helps in vision task, right? So there is a network that is pre-trained on RetinaNet or maybe a huge database, and maybe you can use the same network to detect COVID from X-rays or build a cat or dog classifier. Okay, so we wanted a similar thing, like why it is not possible in audio. It is possible in image, it is possible in speech. Why it is not, it is possible in NLP. Why it is not possible in speech? Okay, so here is our approach to, for where we are saying that we are switched from supervision to self-supervision. Okay, so self-supervised learning, which we'll talk about today, but involves training of 2 models. Okay, so self-supervised learning is equal to unsupervised plus supervised. So there is a component which is unsupervised, and there is a component which is supervised, and the combination of both is self-supervised. Okay, and so self-supervised learning has been creating this breakthroughs in NLP from the past 3-4 years. You might have read about BERT or GPT-2, 3. Then there is vision transformers as well. Okay, but the key point here is that there are 2 things happening in self-supervised learning. So one is unsupervised and one is supervised. And the thing that happens with unsupervised is called pre-training. And what happens with supervised is called fine-tuning. Okay, we'll touch base. Don't worry if you don't understand all of these things, but we'll touch base like how our systems improved first, and then we'll go into the detailed functioning of what is pre-training, what is fine-tuning. Okay, so in pre-training, the model is trained on huge corpus of unlabeled data. Okay, so unlabeled means if you just have the audio data, you can pass the audio data and the system will actually learn meaningful speech representations from that audio data alone. Okay, and in fine tuning, then we say that if you have a limited amount of label data, you can map those learned representations to characters to get your final ASR model. Again, I mean, if you're not getting it, it's perfectly okay, because we will cover in the coming 20 minutes like what is pre-training, what is fine-tuning, and how does wave to wet works. I'm even skipping this slide. I just want you to understand that how our approach changed and why wave to wet worked for us. Okay, so if you compare the two approaches, so supervised learning and semi-supervised learning. So first of all, how much data usage of label data usage decreased? Okay, so in supervised learning, we had a requirement of 10,000 hours of label data, which dropped down 100 times to 100 hours of label data in semi-supervised learning. Now, it is impossible to collect 10,000 hours of data in low resource languages like Bodo, Santali and all, but it is quite possible to collect 100 hours of data in those languages, right? It is quite possible. And then the data acquisition time, as I talked about, we created 4,000 hours of data in 4 to 5 months. And now we are able to create the same 100 hours of label data in 2 to 3 weeks. Okay. And then the third point is go to market time. I mean, how much time does it takes for you to create an ASR model and launch in the market in the production? So earlier it took about 1 to 1.5 years for a particular language, which was now reduced down to 4 weeks. Okay, so just switching the algorithm, just switching the problem, I mean, just switching the way you look at the problem from supervision to self-supervision, we were able to reduce in all aspects. And as I said, I mean, we are reducing the data, but we are not reducing the quality. Okay, so we are still saying that we'll create the state-of-the-art models which are better than Google or Azure that is present currently. So without compromising the quality, we compromise on the data, we compromised on the all of the things, but without compromising the quality of the speech recognition model. Okay, so what it meant for us, the model training cost would come down, the model training time would come down, and the data collection time would come down, and we could launch more models in less amount of time. So I'll give you a statistic. So we were able to create one Hindi model in initial 6 months of the project. But when Wave to Web came in, now we are creating one model every week. So we have open sourced 8 models up till now in 8 Indic languages. Okay, I'll show you where they are open sourced all as well. Okay, and we'll check, I mean, but the point here is that we are able to create 8 models in 8 weeks, and those are production grade models, and almost every model is beating the benchmark of Google, Azure or AWS that is present currently. Okay, so we are creating one model every week. We are creating models that are better than Google and Azure. We are creating models in languages that are not present in Google and Azure as well. Okay, so regarding the models part, so there is a repo. I think I'll link this as well. So this is a Vakyash models repo, if you might have seen. So these are the 8 models that we have created in the past 8 weeks. And with this week also, we are creating a new model on Odia. So Odia is not present either in Google or Azure. Okay, so Hindi, English, Kannada, Tamil, Bengali, Nepali, Telugu, Gujarati. So we have open source models in all of these languages. And maybe tomorrow, by end of tomorrow, you will understand how to use this model to create your own transcripts, or how to use this model to basically on your own data, to fine tune on your own data. Okay, so any questions up till now?
Also, Harvin, as you said, like channel also plays an important role while building the ASR. So most of the data that has been pumped in for this model has been taken from the internet resource. Like it would be around 16 kilo bandwidth, like if I'm correct.
Yes.
So in case like we want to build it on a telephone speech data, do you
Yes.
think like it will have major impact on the performance?
No, so telephone data is on 8 kilohertz, if I'm not wrong, right? So I mean, if you are on 16, if you build a model on 16,000 sample rate, that is perfectly fine. I mean, you need not change anything about the model. In fact, in interspeech, when we participated, most of the data was on 8 kilohertz. We actually upscaled the data to 16,000 sample rate because we wanted to work on 16,000.
Okay.
Yeah.
So when to use WER and CR?
Yes. So see, there are different notations in the industry. So whenever people report results on English, they use WER because WER is a better metric. It's on word error rate. But whenever there is a language which is very vast, which has a very vast vocabulary like Mandarin, people tend to report results on CER, right? Because what happens there is, if two words come together, I mean, if there is in the ground truth, there is a space between two words, but in your predicted text, if two words come together, so even if the individual words were spelled correctly, okay, but still it will penalize you on the WER. So at that point of time, you say that maybe my WER is bad, but for our model, the CER is good. CER is another metric for speech recognition model, which is character error rate. So like we do it on a word level, there is another metric which works on a character level, like how many characters did your model got right. And for models, for languages which are very vast in vocab, we tend to use CER as a metric there. Okay, but there is no hard and fast rule that here you have to report CER, here you have to report WER. It's all on the basis of what you get lower. I mean, if you're getting a CER of maybe 2 in Tamil and WER of 32 in Tamil, then it means that there is some problem with the model understanding the spaces between the words. Okay, because CER of 2 is very, very good if you ask me, and but the WER of 32 is bad. Okay, so in that case, we say that, okay, maybe a model is predicting spaces wrong or something wrong, but our model is predicting the characters right because the CER is on just 2.
Okay, thank you.
Yeah. Okay. Okay, so now we'll move on to the thing that we have been waiting for. What is wave to wake? I mean, because we started this workshop entirely on the basis of we'll train models on wave to wake. Wave to wake is an algorithm and all. But what is wave to wake? And I think even when I first read the paper, a lot of things were very unclear to me as well. So even if you don't get the entire gist of what I'm going to tell you now, that is perfectly fine. Okay. Because it takes a little bit of time to digest things, and it is perfectly fine if you don't get some parts of the paper or something. Okay, but I'll try my 100% to explain each and every point to you. Okay, so first of all, what is wave to wake? So the title of the paper, if you go and check on archive, it is Wave to Wake 2.0, a framework for self-supervised learning or speech representations. And in the intro, the first line is learning powerful representations from speech audio using self-supervision. So there are just two things that I want you to focus here on is the first thing, self-supervised. The second thing, speech representation. Okay. So we are in a process to create some speech representation based on self-supervised learning. Okay. Again, a refresher on self-supervised. What is self-supervised? As we saw in the previous slide, self-supervised has an unsupervised component and a supervised component. Okay. So unsupervised learning in case of wave to wake is called pre-training, and supervised in case of wave to wake is called fine-tuning. Okay, so just understand this thing as of now. In pre-training, we are going to have only unsupervised learning, and in fine-tuning, we are going to have supervised learning. Okay. Again, self-supervised learning, wave to wake, divided into two blocks. One is pre-training, one is fine-tuning. In pre-training, we are focusing on the unsupervised learning, and in fine-tuning, we are focusing on the supervised learning. Okay, so then we'll come, okay, what are the building blocks of any deep learning problem or algorithm? Okay, so the first point is, what is the data? Okay, what is the data you're going to use, whether you're going to use unlabeled data or you're going to use labeled data, whether it's image data, whether it's audio data, whether it's text data, whatever it is. I mean, if you need to build any algorithm based on deep learning, then these are the four building blocks of deep learning. Okay, so the first point is, what is the data? The second point is, what is the model? Okay, so in our case, the model is wave to wake, we all know. The third point is, what is the loss function? Okay, so loss function, I hope you might have gone through deep learning lectures in the prerequisite session, but I just give you a refresher. So loss function tells how far is your prediction from the actual target. Okay, so how far is your prediction from the ground truth? So that is something that the loss function tells us. Okay, and the fourth thing is, what is the metric? What is a metric that you are trying to achieve? What is a metric that you are trying to get better at? Okay, so if you're building a cat versus dog classifier, the metric is accuracy. You want your model to be highly accurate in terms of identifying the cat and the dog. Okay, now coming to wave to wake architecture, as I said, in wave to wake, it is a framework for self-supervised learning for speech representation. It is the paper written by Alexei Bavesky, and there's another person called Abdul Rahman Muhammad, who was the first person in the speech community to actually use a deep neural network on audio in 2009. Okay, so he was the first person to use a deep neural network, and he showed us the way that using deep neural networks, you can solve speech problems as well. Okay, now coming to wave to wake. Okay, so we'll focus on what does the paper talks about wave to wake, what is the architecture. Okay, so they're saying that the speech representations are masked in the latent space and not in the input space. So I'll open this diagram. So what happens is, there is a raw audio waveform. Okay, so you have a raw audio file. You pass it on to a bunch of CNN layers. Okay, so CNN learns the features out of the audio waveform. So as I'm saying, you are passing the raw audio waveform in wave to wake. It's the raw audio. It's not MEL spectrogram or any kind of spectrogram. It's the raw audio that you're passing as an input. When you pass the raw audio as an input, there are a bunch of CNN layers that learns features through that raw audio. Okay, and then once those features are learned, those are continuous features. I mean, if you have an audio maybe of 15-second length, so the CNN will learn continuous features in the latent space. Okay, the point here is, how do you learn about the sequential data? I mean, how do you learn about whether E ki matra comes in the forward or E ki matra comes after a word? Okay, so how do you understand those things. So CNN is just for learning the features out of the audio, but how do you actually make sure that the sequence is also maintained on the audio? I mean, the sequence factor. So the sequence factor is learned by something known as transformers. So transformers contains self-attention layers that focuses on the sequence part. Okay, so CNN focuses on the how do you encode feature, how do you extract features out of the raw audio. Because see, everything the machine learns is either in the form of 0 or 1 in computer. Okay, so if you're passing a raw audio waveform, it has to be in a form in which the machine could learn. Okay, so CNNs are, I mean, there are seven to eight CNN layers, which are also called feature encoders. Okay, because they extract features out of the raw audio waveform. And once they extract features out of the raw audio waveform, they pass on these features to transformer networks to understand the sequence. Okay, because the sequence really matters in speech. As I'm talking about, as I'm talking currently, it cannot be the first word should come at the end, the first and the last word should come in the beginning. The sequence matters, and the sequence part is taken care by the transformer network here. Okay, so how does this transformer network actually works? I mean, I'll just give you a small introduction. So what happens is, whenever the features are encoded by the CNNs, there is masking that is done on those features. So by masking, what happens is, like you have fill in the blanks. Okay, so you mask something out. You so suppose there is a sentence like we are in IEEE workshop. Suppose this is the sentence. Okay, so what happens there is, masking is done after the features are learned by the CNN. So by masking, I mean maybe the IEEE word is masked in this sentence. Okay, and what we are asking the transformer is to predict what is there in the blank. Okay, so we have original audio, we mask something. So masking means that we don't tell the network what exactly is there in that audio, and we ask the network to predict what can be there in the audio according to you. Okay, so I'll again start. So there is the raw audio waveform, which you can call X, that is passed on to feature encoders, CNNs, which is called Z. Then this Z is passed to a transformer network to learn sequence. And how does it learn? It learns entirely on the concept on which BERT also learns. I mean, the concept of BERT and the transformer network here is very similar. The only thing difference here is that this works on the speech data while BERT works on the text data. Okay, so here we are masking certain parts of the audio for the network to predict what can be the next word or what can be the next character you think. Okay, and once the network predicts that, according to network say, okay, I think maybe this is what should come in the audio. Okay, and then there is a layer called Q, which is mentioned here. So which is the quantization module. So this part is a little bit hard to understand, so you need to focus a little bit here. So in quantization module, we are converting the continuous feature encoders to discrete feature encoders. Okay, so whenever an audio is passed to a CNN, the features are in continuous space, but after it passes through a quantization module, those continuous space is broken down into discrete units. Okay, so discrete in the sense, now we know after the quantization module, we know that what happens at t equal to 0.1 to t equal to 0.11. Okay, so once the model from the transformer layer predicts that this is the thing that I think is will come after this word, then that word is matched to the discrete quantized representation using a contrastive loss function. So a contrastive loss function tells like how similar the two things are. Okay, so if you have a discrete representation of any particular character and the model also predicts that character, if those both characters are what the speech what was there in the ground truth, so the contrastive loss is less. If that is not exactly what is present, then the contrastive loss is more. So a contrastive loss gives you the degree of similarity or dissimilarity between the predicted and the actual target. Okay. Again, I mean, if you're not able to understand, it's quite okay. But the only thing here is one part is where we are asking the model to predict. We are masking certain parts of the audio and we are asking the model to predict, like, what do you think should come next? Okay. And once the prediction is done by the model, we are matching that prediction to the quantized representation of that particular timestamp. And if those two things are equal, then the contrastive loss gives you a lower value. If those are not equal, then the contrastive loss gives you a higher value. And over the time, when we train this network, our objective is to lower down the contrastive loss. Okay, I'll just repeat. So speech representations are masked in the latent space and not in the input space. So this is the most important thing, if you ask me, because in other algorithms, what people tried was they tried masking in the input space, like they tried masking on the X, not on the Z here. Okay, so they tried masking on the X rather than the Z. I mean, there is something called as variational autoencoders, if somebody wants to learn more. So in variational autoencoders, the masking is done on the input space and the representations are discrete. But here what we are saying is that we're masking on the latent space. So latent space we get through the output of feature encoders, which happens to be CNN in this case. Okay, and solves a contrastive task defined over a quantization of the latent representations which are jointly learned.
Yeah, Harvin,
People have some questions, I think. Yeah.
Yes.
Yeah, Harvin, I have a small question that this discretization, how they are doing, means this quantization, they will get the continuous latent space, correct?
Yes. So in quantization
Kind of
module,
thing, or?
yes. So in quantization, they have something known as code blocks. Okay, so again, I mean, this is a high-level concept that many people might not understand. So there is a concept called code blocks. So a code block is essentially a dictionary. Okay, so in a dictionary, they have something known as they already have the entries for a particular phonemes. Okay, so using the cosine similarity, they actually try to figure out which is the entry, which is the minimum. On this particular time, which is the entry which has the minimum cosine distance as compared to the input, and whatever is the minimum cosine distance, it picks that entry from the code block, and that is how a continuous representation is converted to a discrete point at there. Of course, there is a Gumbel softmax trick that happens at this step, but it's a very, very, very high level concept. I don't want to discuss in this call because it's okay not to know that thing. But if you want to understand, I think the web-to-web paper gives a very high level overview on that as well. So there is a Gumbel softmax tricks that happens in the quantization module, in which they actually calculate the cosine similarity between the actual latent space and the code blocks that they have, and the one that gives you the minimum cosine similarity, they pick that and they apply the Gumbel softmax to get the discrete representations.
Okay.
Yes, so I want to ask one more question in that direction.
Yes.
So how actually that code works, generating actually? Means it
Yes. So see again, I mean, it's a very high concept. So code blocks is getting generated from the previous learnings. Okay, so a code block is something that is learned in this training. Okay, so code block is a learnable parameter. So for example, I mean, let's take example of a word. Let's say dog. Okay, so there is a sentence that this dog is beautiful. Okay, and this is a continuous sentence. Of course, the feature encoders will pass it as a continuous representation. Now, if in the previous history a dog is seen in the previous sentence, then they would check in the code blocks that in this code blocks whether there is an entry for dog or not. Okay, so if there is an entry for dog, they know that how the dog is pronounced, so they will pick the entry from the code blocks to discretize it. But again, I mean, this thing doesn't happens on a word level in web2vec. This thing happens on a character level in web2vec. So one thing that is very, very important here is that the CNN, the sliding window of the CNN is 25 millisecond, which means that in every 25 millisecond, there will be a prediction. Okay, so if you have a sentence, let's say of length 5 seconds, it will be broken down into 25 millisecond sentences, and on those 25 milliseconds all of these things happen which we just talked about. This prediction will be created, the things will be I mean, the masking that happens on the 25 millisecond window. Okay, so it may be possible that out of that 5-second sentence that you have passed, there is a probability function that actually masks out certain part of the audio. But what is the amount that is masked? The amount that is masked at a single given point of time is 25 milliseconds. Okay, so it happens on a character level. Again, how the code blocks are maintained, how they are created, it's a little bit of advanced concept and requires knowledge of variational autoencoders. But to understand the previous things that the model has learned in the contrastive loss fraction, it tries to keep a code book of those learnings.
Thank you, Arun. Actually, I want to ask that that code generating the code block, that is there means that we are taking help of transcription or web itself?
No. This is right now we have not talked about transcription. This is all unsupervised at the moment.
Okay.
This is only through speech. Okay, so transcription is never in the picture here. So let me make it very clear. We're not talking about supervised yet. We are only talking about unsupervised at the moment. Because see, wherever there is a contrastive loss in wave2vec, it means unsupervised. For supervised, we have a different loss function, that is CTC loss.
Yeah. Okay. Thank you very much, Arun.
Yeah.
Sajal, you have a question. Yeah.
Hello, sir.
Yeah. Hi.
Sir, I have a question that initially you told about masking. So when we are going to train the model inputting some raw data at the starting, suppose you give an example, we are in the IEEE workshop. So we then come R. Openly it may comes after we, it may comes R. So language, so this model can predict R will be the next one. So then there will be, if it is R, then there will be a less amount of error. Otherwise, it will be error. So after a certain time, the error become reduced.
Yes.
After a certain time of training.
Yes. So whatever you have said is quite right. The only thing that is that it doesn't works on a word level. It works on an individual.
That's why I am telling, sir, suppose there is a waveform, we are. So we waveform that if the we waveform is for suppose 50 millisecond or 100 millisecond. So whenever we come previously, so we can break it in some frames. So we are just watching on previous 2 frames, then we can predict that this is we.
Yes.
So this is work like this, or?
Yes. It works like this exactly. The only thing here is, as you said, there is a 25 millisecond window but that window is also overlapping. That is not that is not like 25 first 25 millisecond, then the next 25 millisecond. There is also an overlap between two windows. Okay, so first there is a 25 millisecond, then the ticker moves to maybe 10 millisecond, and then the next window starts from 10 millisecond to 35 millisecond, and then the next window starts from 20 millisecond to 45 millisecond.
That means we are observing the wave. So what is the features in CNN? It is amplitude, frequency, or like MFCC? What type of features? Because I know there is no such kind of MFCC or such kind of features are used. So
Yes.
what type of parameters are taken in CNN?
Absolutely. So as we talked, this is all happening on a raw waveform. This is not happening on MFCC or a spectrogram. Okay, so all the parameters that we talked about are learned by the CNN, right? So I mean, CNN also have a lot of parameters. I mean, what is the kernel? So there is something known as kernel size in CNN. So that is getting learned in the back propagation step whenever it happens. Okay.
Sir, I am just 1 minute.
Yeah.
When we are feeding raw waveform itself, I think CNN itself extracting the suitable features that we cannot compare anything with MFCC or LPCC, I believe.
Yes.
Yes.
Yes. Yes. See, why the notion of raw waveform is here is because in previously all the speech algorithms, what used to happen is people used to map the raw audio waveform to MFCC or Park spectrogram or MEL spectrogram, any kind of thing, right? So that is the only point here was that the people didn't wanted to create MEL spectrogram. They wanted to work on the raw input waveform because they wanted to take in account the noise factors, the direct factors, and all of those other factors, because what they observed was, I mean, this is not written in the paper, but this is from one of the talks from Boveski. He said that when you create a MEL spectrogram, then the noise might not, I mean, the microphone noise or the surrounding noise might not get modeled correctly in that MEL spectrogram or MFCC feature, right? So what they said was they want to create a highly robust model. And in those quest for robustness, they said that they want something which directly works on the raw audio waveform. Okay, so they want CNNs to directly learn from audio rather than learning from the MEL spectrogram, just to increase the robustness of the system in terms of the environment in which the sound is recorded or not.
Yeah.
Okay.
So wave to wake is directly taking the raw waveform, sir.
Yes, it is directly taking the raw audio. The only step that happens is the normalization step before passing on to the model. And that is quite common. Even if you create an image model or a text model, normalization happens. So just the normalization step, but it works entirely on the raw audio.
Okay, sir. Thanks.
My understanding is, for example, MFCC feature extraction takes the raw waveform, and it will give a vector. Those are, we call them as MEL frequency capsule coefficient. Whereas here, CNN itself is extracting the features which are hidden in the given data.
Yes, absolutely. You're absolutely right. And this algorithm is also wave to vec. Okay, so wave here stands for the raw input, and vec here stands for the latent space, the speech representation, right? So how does this thing represents in the latent space? Okay, so wave to vec.
Yeah, Shashank, you have a question? Yeah.
Sir, like when we are masking, it is the continuous representation that's being masked, but we are comparing that with the quantized, I mean the discrete version, right? So the contrastive loss compares continuous to discrete.
No. We are masking the continuous representation, but the prediction done by the transformer is discrete. Okay, and in the contrastive loss function, we are comparing the prediction done by the transformer to the quantized discrete representation.
So like, will there be like a relation between this quantization discretion and then the transformer prediction discretion, so that they both are in the same line or something like that?
Yes, so that is what we're trying to learn here, right? So there has to be a relation between a quantized module and what the transformer is predicting, because essentially what we want is the transformer to predict correctly,
Okay.
right?
Yeah.
So to make the transformer predict correctly, we initially it will do some mistakes, but when when you start penalizing using the contrastive loss, it will try to learn better representation, and that is why there is a difference, direct what do you say? Uh, I mean, significance between the predictions of the transformer and the quantized see, quantized representations are just to create the discrete targets. Okay,
Yeah.
so they are not doing anything in the prediction step. So prediction step only works in the transformer phase.
Yeah.
Okay. So, so as I said, contrastive loss is the degree of similarity or the degree of dissimilarity. Okay. So to calculate the degree of similarity, you need to have something that is predicted by a model, and you need to have something that was original, that was the target, that what you wanted the model to learn. Okay, so here what you wanted the model to learn is from coming from quantized discrete representation, and what is predicted by the model is coming from the transformer.
Sir?
Yes.
Yeah. So we generally feed a raw waveform, and then we
Yes.
get some latent representation for each time step. I mean to say Z1, Z2, Z3 up to Zt, right?
Yes. Yes.
And then that Zt is fed to some quantization. So that will give us Q1, Q2, Q3 with the corresponding timestamps. I mean, sorry, time steps.
Yes.
Right? And that is fed to a transformer with a masked approach.
No,
So that
quantized, no. Quantized representation is not fed to transformer. The continuous representation from the CNN, which was Z1, Z2, Z3 to Zn, is fed to the transformer, not the quantized one. If you check here, the arrow here, you can check the arrow here. The output from CNN is fed to transformer here, but the output from CNN is also fed to the quantization module.
Okay, so at latent space, we have two operations. One is continuous and one is discrete. The discrete part is sent to the loss, that LM loss, I mean the contrastive loss.
Yes.
Okay, so correct me if I'm wrong, this is also similar to that self-attention, right?
Yes, so so self-attention is a part inside the transformer networks.
Okay, with respect to continuous.
Yes, absolutely.
Okay, sir. So at Z, they are doing two parts. One is quantization and one is passing the same thing. I mean, the continuous sequence.
Yes.
So that it captures context information properly. Am I right?
Right. Absolutely.
Okay. Thank you.
So, but the final output is some transformer, whereas quantization is only used for calculating the loss, right, sir?
Yes. So the final output, the learned parameters are within the transformer. The quantize is just to create the targets. Okay, so it has no feature inside learning. Okay, it has some feature inside learning, but again, I mean, you can think of that way, that it is just to create the final targets.
Okay. So yeah, so this quantized representation, this dimension is a hyperparameter or what? When you are doing this quantized, you'll get a hyperparameter, no?
Yes, the hyperparameter is the
number of dimensions, means dimension of that quantized space representation.
So the hyperparameter here is the number of CNN layers, the first hyperparameter, then the number of transformer layers. Okay. And within that CNN also there is a hyperparameter called the window size. As I talked about, 25 millisecond. You can have a 30 millisecond, you can have 40 millisecond, you can have 50 millisecond, based on the language on which you're trying to build the system. Right? But what they found out, that 25 millisecond just works well for all the languages. Okay.
Yeah.
Yeah, Harvin, okay, just couple of questions. I know this slide has taken more time. Yeah. Yeah. So, okay, I do understand the vertical axis gives the deeper number of deeper layers, and horizontal axis gives us the temporal axis. So, what would be the number of contexts with reference to temporal content? 25 milliseconds is a frame size. So, how many such frames are used, say, for predicting a mask?
So, so there is something known as masked probability. That is another hyperparameter in which you can say like, so if my mask probability is 0.5, let's say, and if I have a 5-second audio length, then it means that what I'm saying is that I want to mask 50% of the sentence without replacement. Okay, so which means that essentially 2.5 seconds of the sentence would be masked. And in this prediction, there will be predictions based on the fact that how many number of units are getting masked. Okay, as you said, I mean 0.5. If the probability is 0.5, then you can expect the transformer outputs to be have I mean whatever is calculated by the mask probability. So that is another hyperparameter that you can.
Okay. So for example, what is the typical probability value that you people have used while you build the system?
So a typical probability value is around 0.3 to 0.6.
Okay, so that is you keep 60% of the frame to predict the rest 0.3. Is that correct interpretation?
Yes, yes, that is a correct interpretation.
Okay.
Yes.
Okay, so okay, CNN with reference to this quantization, one more question.
Yes.
So typically, how many number of quantization levels are used? Like, so is it somewhere closely connected to the number of phonemes, or loosely? I'm talking about.
No, so no. See, right now, whatever we are talking about is independent of the language, independent of phonemes, independent of each and everything. Okay, so nothing dependent on any type of language.
Yeah, there is no labeling, I agree.
Yes.
So, but you have to put them in bins, right? So 30, 40 bins, whatever be it, like, yeah.
Yes. See, I'm not quite sure on the level, but there are code blocks, as I said, in quantization module. So these code blocks are in the range of 2 raised to power 16 to 2 raised to power 32. Okay, so these are dictionaries that are kept by Web2Vec while training the algorithm.
Okay.
And these are in the range of 216 to 232. But again, I mean, I don't actually understand. I mean, you're asking about the number of layers in the quantization module.
No, this quantization essentially will be, as you said, like the continuous quantity, right? Has to be classed into, say, some finite numbers, basically.
Yeah.
Finite number of quantization levels.
So Deepak said there are 320 code book entries and there are 2 code books. Yes.
Okay.
Yeah.
Correct.
Okay, thank you.
Yeah. Okay, so I think just to revise, I can understand that this is a huge bunch of a different world, and maybe a lot of people might not get it, but it is okay. I mean, we are able to here to get a little bit of understanding, and when you read more, you'll understand more. Okay, so just to revise, the speech representations are masked in the latent space and not in the input space, which means that the output from the CNN, that is the output from the feature encoders, are masked and not the raw audio input. Okay, and the quantization module here is used to convert the continuous representation to discrete representations to calculate the contrastive loss, which tells you the degree of similarity between your predicted values from the transformer and the actual target values. Okay. Yes, so I had another slide. I think it talks exactly the same thing. And inside the training, as we talked about, masking is not done to the inputs that are passed to quantization module, as we have already discussed, and a lot of people has asked as well. And during pre-training, the representations of the speech audio are learned by solving contrastive loss. which requires to identify the true quantized speech representation for a mask times. I mean, you can have a different vocabulary of what we talked about, but this is what exactly is written in the paper. But this is the overall functioning of wave-to-vec in the unsupervised fashion. Okay, so we'll come quickly to what is supervised then. I mean, how do you do supervised learning? We'll talk about that. So as I said, I mean, there are two steps. So one is pre-training and the another is fine-tuning in wave-to-vec. So as we also talked about in deep learning, we need those 4 building blocks. So in pre-training, which is an unsupervised step, so what is the data? So in pre-training, the data is unlabeled data, which we're saying is only unlabeled speech data, which is only audio data. And the audio data here can be from multiple languages. Okay, so you can think of pre-training as something that maps speech to the speech data to some latent representations. So these latent representations can be phonemes as well for a particular language. Okay, it can be phonemes, or it can be any meaningful thing that could be learned from the input waveform. Okay, and then what is the model? We already know, we've seen wave-to-vec is the model in pre-training. And what is the loss function? We have talked about contrastive loss. Diversity loss, again, is a little bit of high level concept, but it's mentioned in the research paper. We are not going to go deep into diversity loss because it's a penalty loss function. It's not a main loss function. Main loss is contrastive loss that Anirudh covered yesterday. And then what is the metric? We are trying to get accurate predictions. So here the metric is accuracy. Okay, so we are trying to measure the accuracy of our systems, and we are saying that if we get a system which is able to predict 60% or 65% time correctly, then we have a good system. Okay, so in pre-training, if we get an accuracy of 0.5 or 0.6, which essentially means 50 to 60%, then we are saying that we have a good speech representation system. Okay, so we are not aiming for 100%, we are not aiming even for 90%, we are not aiming for 95%. Okay, we are just aiming for 60-70% based on the fact your mask probability is 0.5, or ranges from 0.3 to 0.6. Okay, if your mask probability, let's say, is 0, I mean, you're not masking anything, then you can achieve 100% accuracy. Your network can learn all sorts, I mean, not learn the representations of speech, but learn the speech itself. Okay, but that is not useful to us. What is useful to us is how the network is predicting when you apply a mask. Okay, so when the mask probability is between 0.3 to 0.6, we are aiming for an accuracy around 60 to 65% in the pre-training step. That's it. Okay, so now we move on to fine-tuning. Like, what is the fine-tuning step? So what is the data in fine-tuning? So in fine-tuning, we have labeled data. Okay, and in this case, we are saying that since we have already done an unsupervised task, we do not require huge amounts of labeled data. Even 1 hour is enough. Even 10 hours is enough. Even 10 minutes is enough. Okay, so even if your data has covered all the vocabulary, all the phonemes, even within 10 minutes you are able to cover. You can have just 10 minutes of label data, or 1 hour of label data, or 10 hours of label data to do the fine-tuning step. Okay, so in fine-tuning, data is label data, which is audio data plus corresponding text. And the audio data has to be from the language from which you want to create an ASR. Okay, so this is a very important thing. So in pre-training, you can have data from multiple languages like Hindi, English, Tamil, Bodo, Santali, and all. So once those speech representations are learned, then in the fine-tuning step, you try to map those learned representations to output characters. Okay, to output characters. For that, you need to have labeled data. Okay, and you need to have label data only in the language in which you want to create an ASR. You can also create a multilingual ASR. I mean, you can have a mix of Hindi and English symbols. But then if you have a mix of Hindi and English symbol, you should not expect the model to predict for Tamil language. Okay, so you have to make sure if you want to create a Hindi ASR, you need 10 hours of label data in Hindi. That's it during the fine-tuning step. Then what is the model? The model stays the same. The wave to X stays the same. It's just that there is a linear layer attached on the top of this network. The linear layer has outputs which are equal to the vocab or your dictionary size, like what you're trying to predict. Like for English, there is a dictionary of 26 characters, right? It can either be A, B, C, D. So what you're trying to do is you're trying to map the latent, you're trying to map the learned speech representations from the pre-training phase to a particular character, right? This is so if you have a cluster inside a pre-training step, you want to map that cluster to an output label. So how do you do it? In the fine-tuning step, by providing the label data. So you're saying that when I provide the label data, that cluster would be mapped to the either A, B, or C, or D. So you have a dictionary in which you specify what is the expected number of outputs from the model. Like suppose in a cat and a dog classifier, what can be the expected output? The expected output can either be a cat or either be a dog. So your number of classes is 2. So the number of classes in the fine-tuned model when you're doing it on English is 26, because your prediction can either be of in 26 characters. It can either be A, B, C, or D. Okay, so in fine-tuning is just having a linear layer on top of the wave-to-wake architecture. So linear layer, the number of nodes present inside the linear depends upon the output of the language in which you want to create the ASR on. Okay, so for example, in English it is 26. So the number of units in those is 26. And then what is the loss function? The loss function is the CTC loss function. Okay, as Anirudh discussed yesterday. So CTC loss function, you can have multiple outputs coming. You can have multiple outputs coming from a model. Like if you have a hello, then you have H coming in multiple times, then E coming in multiple times, then L coming in multiple times, and then you combine all of them together to match it to your final target, and then calculate the CTC loss function. And the metric inside fine-tuning that we are trying to optimize is WER. Okay, so we are trying to optimize the word error rate in the fine-tuning phase. So we are saying that the the test set, I mean the model which has the least WER on my validation set, I would try to save that model as my final model that would go into production, or that I would use. Okay, so these are the two steps. One is pre-training, one is fine-tuning. So pre-training is learning from unlabeled data. Pre-training is learning powerful speech representation. And then fine-tuning is mapping those powerful speech representation to labels by using your label data. It can either be 10 minutes, it can either be 1 hour, it can either be 10 hours, depending upon how much data you have for a particular language, right? So the problem with those 10,000 hours of label data is now gone. Okay, we don't require 10,000 hours of data in a particular language. We're saying you just give us probably 50 hours of data or 100 hours of data in a particular language, and we will create a production grade model for you. Okay, so I think this was what I had from the slide perspective. Maybe in the evening we'll go through what is there in the code. Let me take some questions that are okay, no questions. If anybody wants to ask, then please go ahead.
Arvind, what is the fine-tuning architecture is? We understood that pre-training architecture.
So fine-tuning architecture is exactly same. It's just an addition of a linear layer at the end. It's exactly same.
When you say linear layer, it doesn't have non-linear activation function. That's what you mean by?
Linear. When I say linear layer, it means that a final layer in the step that your outputs, like there is a flattened layer in Keras. I mean, if you know, right?
Yeah. Flattening is about converting 2D to say 1D.
Yes. And then after the flattened layer, you have an output layer which is equal to the number of neurons.
That is fully connected layer.
Fully connected layer. So you can say that a single fully connected layer at the top of the entire pre-training architecture. That is the fine-tuning architecture.
That's more like a classification layer, right?
Yes.
Character is the classification. Yeah.
Yes, absolutely.
So we get C from that pre-trained model. You feed that C representations to the linear layer or fully connected layer, what you're talking. Then it puts in the characters.
Yes. So during the fine-tuning step, what we say is that the audio that you are passing, because that audio is also labeled, right? So in that audio, now I know that this representation represents A or this representation represents B. So we are just trying to map the representation to the characters that we are trying to predict.
Yeah. And there we follow CTC loss. Yeah.
Yes, CTC loss, because there can be multiple, because the window is 25 millisecond, right?
Correct.
So in this 25 millisecond, there can be multiple predictions of the same character, right? So H can be predicted like 10 times, E can be predicted 15 times, and then you have to merge them together to get an output that is there in the ground truth, right? So then you...
Typically speaking, a number of frames for characters would be more than say number of frames for a phoneme, because usually we do follow some 40 phonemes in a given data. So the characters, if we take English character, is quite less, 26 characters.
Yes.
So we can expect more number of frames in a audio data.
Yes, absolutely.
So in every 25 millisecond, you will get around 26 character probabilities, is it?
Yes.
Some dot and all this will be maybe included.
Yes, absolutely. In every 25 millisecond, we'll get 26
probability values. Maybe more than, not 26, maybe more than that.
Yes, more than that, because there is a prediction for the space as well. And then there is a CTC token, which is underscore in this case, right?
Yes.
So suppose if you have a word like hello, in which L is repeated, L comes twice, right? Now, how do you know that 15 L's have to go to 2 L's or a single L, right? So there is a CTC token that is
underscore
between the two characters as well.
Okay, so the space is for belongs to silence region, correct? If I'm not wrong.
Yes, so space is for silence. It's also in the ground truth, like what is considered as the space, right? So if there is a space between I and M in ground truth, then only your space will be predicted as a part of your output.
Okay.
Hello, sir.
Yeah.
Sir, in unsupervised learning and the training data, the algorithm may think that there are huge number of characters, because every time it's just look into the waveform, it will come differently, because there are different type of speakers, different type of utterances are there.
Yes.
But in case of a supervised learning, there we are giving the transcription, means label data, so it knows that there are 50 character or 40 character. But
yes.
how it will map that those? But in unsupervised, it may be 1,000 of characters or more than thousands of characters.
Yes.
So you have to map those 50,000 character to 50 character.
Yes. So suppose in unsupervised step, in the pre-training step, first of all, you cannot have 15,000 as a space, but let's say if you have 1,000 space, okay? So you have 1,000 powerful representation. Those are discrete representations for a particular character, like you're saying, right? So then in the fine-tuning step, the diversity of data also matters, okay? You cannot have data from a single speaker in the fine-tuning step, okay? The diversity step is still there. So if I speak something, if I speak A as A and you speak A as A, suppose, okay, and in the pre-training step there are two clusters, one is for A and one is for A, then in the fine-tuning step the model will understand that this A and A essentially represents the same thing. Okay, so it essentially represents the same thing in the final output, that is A. Okay, so then it says, okay, in the pre-training step, A and A has separate clusters. So let me combine this cluster to get a single representation for A. Okay, so whatever we're talking about, the diversity in the fine-tuning step also matters. You cannot have a single speaker speaking 10 hours in the fine-tuning step and then expect the model to learn different representation. Okay, so still the diversity factor is still present in the fine-tuning space.
Yeah, and also it depends on the latent space variable size itself. Yeah.
Yes.
So yeah, at the pre-training stage. Yeah.
Yes.
Sir, I have a question. Like, once we have trained a pre-trained model, that is, for example, say 10,000 hours of data, and now we have to fine-tune it for two different languages. Say one language has 26 characters, and the second has 50. So same fine-tuned model will be mapped to 26 and 50, right? Or we have to do some other things or tuning in the pre-trained model also.
No. Pre-trained model you just train once. Okay. So what the expectation from a pre-trained model is that irrespective of the language, irrespective of the environment and all, it is able to create powerful speech representations. Okay, that is the expectation from the pre-trained model. The expectation from a fine-tuned model is that whatever the latent space that has been learned for those speech representation, I would be able to map those to a characters. Okay, so essentially, like what we have done is we have trained a pre-trained model on 10,000 hours of 10,000 hours of data that is only on Indic languages. Okay, so I mean, in the afternoon maybe we'll show you the model. So it's called CLS-RIL 23, in which we use 10,000 hours of data from 23 different Indic languages. Okay, so suppose another factor here is, so suppose in pre-training you just take the English data, suppose, okay, and now you want to do fine-tuning on Hindi. Now you would say that how it is possible that you are giving English data only in pre-training, but you want to fine-tune on Hindi. But when you start doing experiments, when you'll understand that you can still fine-tune a Hindi model based on English pre-trained model. Okay, because the objective of pre-trained model is to learn speech representation irrespective of the language that you pass. Okay, so it is quite possible that you train a pre-trained model only with 10,000 hours of English, and then you fine-tune a model on Hindi language. It is quite possible.
Okay.
Also, Arvind, if suppose I want to train, let's say, Hindi and English combined, or if I keep increasing the number of languages, the expected output from post the fine-tuning, you think like there would be compromise in the accuracy as I increase the number of language outputs from the ASR?
Yes. So see, if you are creating only for English, then your output, I mean, in the fully connected layer, your output number of neurons are 26, let's say, suppose. Okay. If you're creating a English model, now Hindi has 70 characters. Okay. So then your final layer would have 70 plus 26.
Correct. Yeah.
Which is 96 characters as the final output. Then you need more data.
Yeah.
Okay? Then you need more data to get a more accurate system. Okay, so you can have a single model outputting English, Hindi, Tamil, Bengali, but as your vocab size, as your final layer output size keeps on getting increasing, your requirement for the label data also starts increasing.
Right? Yeah. Yeah.
Yes. Any more questions?
And also I've seen like Step has participated like just using the pre-trained and fine-tuned models without even language models.
Yes.
That's really interesting. Like even without using imposition of language model, already the system would give say 90-95% accuracy. That's quite interesting. I mean.
Yes. So a language model, maybe we'll discuss a little bit more tomorrow. For participants that do not know, so a language model can also be applied on the top of the output from ASR output. Okay, so what a language model does it checks whether your sentence is meaningful or not. Essentially, I mean, a language model is something that learns from a text corpus only. Okay, so language model predicts what can be the next word, what is the probability of these two words coming together. Okay, so that is what a language model is. We'll discuss maybe tomorrow in a little bit of more detail. Yes, in those competitions we did use only the ASR output, okay, and not the language, because see, you can create a wonderful ASR if prior to hand you know what is the output words that you're going to get in the final output, and that can be bettered by just a language model, as Anil showed yesterday. So machine learning was converted to mushroom learning and all in the ASR model output. But beforehand, if you know that a machine learning would come in the, I mean, speaker would speak about machine learning, then you can adapt your language model to that to actually predict mushroom to machine. But that is not quite useful. I mean, that is useful for domain specific data, but not quite useful for generic things. So the models that we have created are generic. I mean, you can test it on your voice, you can test it in any domain, and we expect them to work better than Google or Azure anytime.
Mm-hmm. So where do you stand as of now? If you've done a comparison, let's say with Google or Azure, so where does the Wakian model stand in terms of accuracy or say word
Yes. So in terms of word error rate, I have a slide which is kind of not updated, but we will release the final statistics coming on. We have released the final models, but we are writing papers in which we release the final statistics. So the current results, as you see, these are results on a Hindi pre-trained model. These are not results on our 10,000 hour pre-trained model that we have. Mm-hmm. But even in this, we are still, I mean, close to Google or beating Google in languages.
Yeah, couple of languages. Correct.
Yes. But still, for all these models, we will release the original statistics with the research papers. Those are currently in progress because due to workshop preparations, we could not manage to write all of this. But we managed to open source all the models. But we'll provide all the statistics on them.
So still what is released is 4,200 hours, right? It's not 10,000 hours.
Yes, so 10,000 hour is this model, pre-trained model. So this is RIL, which is pre-trained on 10,000 hours of data, which is across 23 different Indic languages. Now, if you want to create a Hindi specific ASR, in the fine-tuning step, you just need to have Hindi. So we are saying that we have a Hindi model that is fine-tuned on 4,200 hours of data. And then we have a English model which is fine-tuned on 700 hours of data, and so on for other languages. Right? So what we have seen generally is that more the number of fine-tuned hours you have, the model tends to work better. But there is no hard requirement. As I said, you can create a model from 100 hours of data like we did for Gujarati, Telugu, and maybe Nepali as well. Right? You can very well create a model with 10 hours of data as well. But it's just that the accuracy of the ASR improves if you have more label data in the fine-tuning step.
Okay. Any more questions?
Sir, I had one question. For that, like if you take that fine-tuning part, there is like around 560 hours data for Kannada, suppose. Like all those data is used for just one layer, right? That the fully connected layer that you are telling. The last, all others are locked. Those parameters will not learn them again.
Yes. So a very good question. So in the fine tuning step, uh, there is an option for you to freeze the model. Okay. I mean, freeze the parameters that were learned in pre-training step and just learn the parameter of the final output here. Okay. But if you have a multilingual system, if you have a multilingual pre-trained model, let's say CLS RIL, then those parameters are for multiple languages. Okay, it's not for a single language. So in the fine-tuning step, you need to actually switch on your entire network so that your parameters get adjusted to that particular language. Okay, so in the pre-training step, you can have representations for English, Hindi, Tamil, Kannada, Telugu. But in the fine-tuning step, if you just need those representations for Hindi, then you switch on the entire network to learn those specific parameters only for Hindi. Okay.
Okay.
I mean, if I am able to find, I mean, there was a good.
So when you say switch on, like it's only you're filtering Hindi data to going for the pre-training, or
No, switch on means the parameters that were learned during the pre-training, they will also start getting learned in the fine-tuning step as well.
Okay, it's like kind of running few iterations on top of the pre-trained model itself.
Yeah. Yes. But the point here is that the weights initialization is not random in fine-tuning. It's the same that was learned in the pre-training step.
Correct. Already it is trained to a level. You just again sort of fine-tuning on the pre-trained model. Yeah.
Yes.
But it may require more data, no? No, it will start from that side. It may not require, is it? Because more number of parameters it have to learn.
No, because it starts from an already pre-trained model and the weights are adjusted in the case. It doesn't require more data in the fine-tuning stage. Okay, as you see that in this representation, there are different representations for English, then Chinese, then French, and there are some representations that are common between these two languages. Now, if you want to just create a model for, let's say, a French ASR, then you would switch on the entire network so that it specifically learns for the French, because I mean, the English-Chinese representation within the French representations may or may not add any value to it. Okay, so you want to learn only from the French representations.
Also, Arvind, the same pre-trained networks are used for speech enhancement purpose and also speech-to-speech translation also. So any idea on that? Like, of course, it's like an encoder network. It has encoded to a latent space, and we need to decode it to the speech file. I mean, is that the way the speech enhancement is handled?
So, see, a couple of experiments are currently in progress because this is a very new architecture. This was released way back in September 2020 only. So, a couple of research areas are present, like emotion recognition, right? How do you recognize emotions from the speech? Then intent recognition. What does the user wants to do, right? Again, I mean, those are in the research purpose. That for that, Facebook has released a new algorithm called HUBERT, which is specifically for the speech ecosystem, which means which works on these tasks like emotion recognition, then what the user is trying to do and all. It's also basically the entire network is similar to wave-to-wake, but there is a small change in how the pre-training step is done, because we are using contrastive loss in wave-to-wake. Here, instead of contrastive loss, clustering is done in pre-training step. That's the only difference in HUBERT. So as I said, I mean, speech recognition, generation, and compression. So whatever you are talking about, speech enhancement and all of these things are active area of research in this network as of now. So this was released only recently, June 15, 2021, just a month.
They've released a model, is it? Not the code.
No, they have released model plus code plus pre-trained models as well.
Okay. Yeah. It's similar to wave-to-wake framework.
Yes, it's entirely similar to wave-to-wake. Yeah, as you can see, the CNN encoder, raw waveform, the masking is done, the output of transformer. The only thing difference here is that instead of using a contrastive loss in the pre-training step, clustering is done in the pre-training step. Okay, so you can achieve unsupervised learning in multiple ways. Either you can do a contrastive loss fashion, or you can do a clustering mechanism as well in the pre-training cell. I mean, clustering in the sense like you try to create have multiple clusters of the similar speech audio, like A and as we talked about, right? So you try to classify them into similar clusters. So they use k-means clustering on MFCC during the pre-training step to learn on the, k-means clustering. Okay, and there is some MFCC element involved as well from the raw input waveform. But yes, these are active areas of research. Even wave-to-wake is a very new architecture, and that is why even if a lot of people don't get what it does, it is fine. Because over a period of time when you start using it, you tend to learn about more things, right?
Yeah.
So even on the first time when we used the architecture, we also didn't know what is happening. Even at that point of time, it was a black box to us. Right? Only when we understand the power of wave-to-wake, what it is capable of, and then only we got some inquisitiveness, like how does it works, how does it runs, and all of the steps.
True. Right? Jagbandhu?
Yeah.
So what do we plan thereafter?
We Anirudh have inference part. He will take.
Okay.
Maybe
Now,
after
maybe
10-15 break we can give.
Yeah. So okay, thank you, Arvind. You clarified most of the questions with so much of patience, and your talk was really good. I hope there are a few more questions, I think.
Yes.
Hello, sir.
Yeah.
Sir, I have a different type of question actually. So suppose we are making a model, DNN model, and training the model with huge amount of supervised and unsupervised data learning. Then whenever we want to use those kind of ASR system for commercial use or personal use, then those type of processing at the time of training and decoding is taking GPU and lots of time to execution. But whenever someone speak in front of a ASR system like Google and something like this, then his data should be computed in that particular network. So that means we need a permanent GPU or such kind of things to run those kind of ASR system for some commercial use or for some real-time use.
Yes. So see, deep learning algorithms, the only limitation is the hardware capable compute. Okay, so you need to have your own hardware, or you need to have your good hardware to train models, to infer your models, and from the hardware section, particularly GPU. Okay, because all of these libraries like PyTorch and TensorFlow work well on CUDA-enabled GPUs. Okay, so I'll give you a small demo. Okay, so I think we have a little bit of time here. If the website is up, is my screen still visible?
Yes.
Okay, so I think the website is down. Maybe tomorrow we'll give you a small demo on the real-time working of our ASR models. Okay?
Yes.
And we'll give you we'll tell you on what type of hardware on which these models are deployed. Okay, so training models is one thing, deployment of models is a whole different ball game altogether. But yes, you're right. For these algorithms, the GPU is a must, whether you're doing an inference or whether you're doing training. But it doesn't mean that the inference doesn't work on CPU. It works on CPU. It's just that it takes a little bit more time.
Yes, sir. Because I want to know that's where there are some train data, test data for decoding. So we have time to execute this model. But whenever we are real time, suppose we are in Google, we are saying something in Hindi or English, and it's making its text in real time. That means those speech input are taken in real time and execution within 1 or 2 seconds. So that's why my question is, whenever we want our output within 1 or 2 seconds from the user end, then what type of hardware or what type of setup we need?
Okay, so this question will be answered in detail. I think the hardware that you have currently, the one Tesla T4, right, and 8 CPUs, that is enough for real-time inference. And we'll show you a demo, a real-time
Okay,
demo,
okay. Yes.
in which you will speak and the letters will be displayed. Okay.
Thank you.
Samudraj, yeah. Samudraj, sir. Yeah. So, thank you, sir. Arvind, yes, complimented. Sir is complimented.
Thank you. Thank you.
Thank you, Arvind. Thank you so much. So, shall we have 10 minutes break and then we'll start with the Anirudh session?
Yeah, sure.
Yeah. Shall we meet at 12:05?
12:10.
12:10.
Yeah. We'll meet at 12:10.
Okay. Okay. Thank you, everyone.